today?
Well, here's the thing. Just be a ninja and like wake up at 3 a.m. and be good to it.
I, no joke, had an email from Joe this morning in my inbox that she wrote me at 3 a.m. No clue why she was up that early. But it was,
Who did?
I had an email from Joe, timestamped 3 a.m.
Maybe she's up, maybe it was just a funny computer thing.
I don't know. Travel to different places. What is that in the clothes like?
He has to post the integrity link.
And everybody else has a handout for today. Oh, it's fine, okay. I'm gonna turn off this front one, right up there. So, the homework 4 we're collecting today, and I'll write another one soon, and a little bit on the Poisson random variable and moment generating function. That'll be due, could be due Tuesday, but you could probably also take it on Thursday. What we're looking at is we'll have the material today, and that's really going to be the material that is on the first exam. We're going to have the first exam will be the first, it's 4 chapters, right? So some introductory material, things on counting and probability, and then there's the discrete random variables that will be on that material. Before the exam at the end of next week, so next Thursday, we'll do some review of that material, talk about which formulas would be on an exam and how that would be organized, and give out some practice problems and things like that. Right? There are a lot of details in the book and a lot of different things that we've covered, and so the exam will cover a lot of those things, but not necessarily every last detail. I'm trying to make that clear about that. The homeworks, which we've done in lectures, would be good study material, and I have solutions to some of the practice problems and the other problems that you've done in the homework, updated before it's time to study for that. So, okay. Today we're going to talk about Poisson random variables and something called moment generating functions. After this class, in here at 12, I'm giving kind of this introductory R session, like I mentioned before. Maybe you've seen some announcements about that. So this is just intended for the broader St. Michael's community. The first session includes things with how to install R in our studio and get it going and save files. So in that, it's a little redundant to what you've seen. The handout for that we used in our class to kind of introduce it is kind of very much similar to the one that's there. It'll do a few more examples. So it's redundant. You're welcome to say if it works for you. It should be recorded also for integrity, and the other, there's a little bit more on loading some different types of data sets. But that, again, I'll make that available. So some other people probably could be coming in a little bit before noon, but if you can stay and want to, that's great. The second and third ones, which would be the next Thursday and the Thursday after that, we'll do a little bit more with statistical models, a little more with estimation, and be a little bit different. Right. So that's ongoing. Right. So today we're going to look at the Poisson another one of our discrete random variables. And it takes, if the random variable is called y, the values it takes on are positive integers. And it generally counts the number of occurrences that happen in a short period of time, or in a small area, or in some volume of space. So the number of outcomes that are occurring in some interval of time, number of outcomes. Interval of time, or distance, or area. And it applies in a few situations. Generally, that one thing is happening at a time, right? And there's a certain constant rate that's kind of happening across time. So there's some rate of things happening called lambda. And this model for this type of things, the probability that you have a certain number of outcomes, 0, 1, 2, 3, and going on, has a formula, and the formula is lambda to the y e to the negative lambda over y factorial. With the, that 0 factorial is defined to be 1, so if y is 0, there's just that in there. And so that gives us a probability distribution. Now, a couple things to as a formula there, right? Do these probabilities add to 1 as we go across the entire range of outcomes, right? Across all these outcomes, we want these things to add up to 1. Do they actually add up to 1? So that's the first question. Do the probabilities add to 1? Or we would want to see overall the range of all these cases, as the probabilities, do they add to 1? That's what we want to check. That should be 1. And so we're going to put in the formula for that, lambda to the y e to the negative lambda over y factorial. So everything is here, adding up all these different terms. So we want to simplify this a little bit. What's one thing we can do to simplify this? How about that e negative lambda? That's the same for every single term. So we can pull that outside of the summation. E negative lambda. Can multiply each and every single term. So lambda to the y over y factorial. Now that expansion, that series, the sum from y going to 0 of lambda to the y factorial, is a special series. And in fact, that is the equation, the Taylor series expansion for e to the lambda. And so you add the exponents up there, right? So it's e to the negative lambda plus lambda, so it's e to the 0, which is just 1. So in fact, the probabilities do add to 1. These are, everything in this is positive, so they're going to be greater than or equal to 0. They add up to 1, so this is a probability distribution. Although it goes off to infinity, as you get bigger and bigger, you have that y factorial in the denominator. The y factorial gets big really fast. Right? 10 factorial, 10 times 9 times 8 is something. The computers compute that, but you get up near 100 factorial, and the computers have trouble storing that big number, even in memory. Right? They have to do it on a log scale or scientific notation scale that it gets so big. It dominates. It's in the denominator, so after you get out a certain number of values, those probabilities are going to go down pretty fast. Right? So let's look at the handout has some examples. So it's here's a description of the process that gives us a Poisson count One classic kind of example that is this is almost created for is radioactive decay of radioactive unstable material. So NCTF is the National Council of Teachers of Mathematics, and every year they have a yearbook that presents examples and discussions about teaching different topics. In 1981, it was on probability and statistics. So I think they've had another one on probability and statistics since then. But in that example, for example, it says that in that article, it says that if you have a kilogram of radioactive plutonium, not plutonium, but uranium, right? and you have detectors around it, and in about 7.5 seconds, which is about 1/8 of a minute, I don't know why exactly they chose that 7.5 seconds, but it's 1/8 of a minute, at the rate of particles coming off of these things and being detected is 3.87 per particles in that time period, right? And here you go. And so the general formula for the probabilities follows the Poisson process. So, even if a few particles come off of this kilogram of material, there's billions of particles of atoms in there. And so there's really no difference. The rate of decay of radioactive things is fairly constant over time with some variability. Right, so we would have the general formula was probability that y equals lambda to the y e to the negative lambda over y factorial. So when it's 0, lambda to the 0 is just 1. We have e to the negative lambda, and the 0 factorial is 1. So that's the probability. The chance that you actually would see 0 is pretty rare. The chance of 1, right, you get a 1 copy of lambda here and a 1 factorial down there, so it goes up to about 8% is the probability you're going to see one thing. Two things, you get 3.87 squared, now you have 2 factorial down here, and it goes up at y equals 3, right, everything is just 3 factorial in the denominator there. 3 times 2 times 1 is 6. What's going to happen to the probability when y equals 4? Is it going to keep going up? No, so it's going to start going down, right? The probability that y equals 4, all right up here at the top, the probability that y equals 4, the lambda to the 4th, e to the negative lambda over 4 factorial. And now lambda is 3.87, but now we have 4, so we start dividing by things that are bigger. Right? So this would be 3.87 to the 4th, e to the negative 3.87 over 4 factorial would be 24, 4 times that. And whatever that number is the probability. And this is a graph of those different probabilities. 0 up to 20, and we can go off forever. Right? You could have a billion particles pop out of this. But the chance of that happening is so extremely small that we don't care too much. If this is really the rate that is happening, it's really Poisson, the probabilities are still going to be pretty accurate for the outcomes of 0, 1, 2, 3, and so on. So here's the 0, 1, 2, 3. Here is 4. Probability that y equals 4 is whatever that height is. So it goes just down a little bit. And after that, it drops because you get another 3.87 on top, but then you divide by 5, divide by 6, and it starts getting it down. So that will give us an example of what's going on with the Poisson. But any questions about the formula? Now, we look at different characteristics of these things, right? So a Poisson rate, it turns out that the mean is lambda and the variance is lambda, so the standard deviation is the square root of that. So if we're in this radioactive particle example, the mean is 3.87 particles on average. And the standard deviation is about 1.97. If you think about the mean plus or minus a couple standard deviations, 2 times this is about 4, right? And the mean minus 2 standard deviations is about 0, right? So 0, 1, 2, 3, 4. Going up 2 standard deviations is about 8, right? 2 times this is about 4, and that's about 4. It's about 8. And most of our places that we have any probability that's much bigger than 0, right, happen, below 10, 0 to 8, 9, 10. Right? Most of our outcomes we would see if we took different samples of this particulate, right, are going to be in that range 0 to 8, 0 to 9, 0 to 10. Occasionally we'll get a few more, but a lot of the time we're going to get those numbers. And in the long run, the average number of particles is going to be 3.87. So if we really wanted to get 3,870 particles, we could do this for 1,000 7.5 second intervals. I don't know how long that would be total. So, we could run the reactor and collect these particles in the counting detector for a few weeks and get this large number of particles if we wanted to study that big number. Now that we're going to figure out, we're going to show that this is actually the truth, that these are actually the mean and variance. We're going to go through some work to do that. But one neat thing about Poisson is that as you join together areas or intervals or accumulate Poissons and add in together independent realizations of this one, is that it stays as a Poisson variable. So if you looked at 75 seconds instead of 7.5, or that's 10 more added together, the rate goes up by that factor of 10, right? So now you would expect 38.7 particles in 75 seconds. And the important fact is it stays as Poisson. Not all variables stay in the same kind of family, same probability structure as you add them together. This one does. And so it is again Poisson, random variable. And so now the variance is known by that formula and the standard deviation. So over time, we can get some idea of, here I put plus or minus 3. That's kind of at the extremes. You can also think about plus or minus 2, right, as giving some range of values that you would get in 75 seconds. So here are some plots of the probabilities, the probability on this side, versus different values of C. So this is a Poisson with a larger mean. At the beginning, there's very little probability. Right? The probability of 0 is just e to the negative 38.7. Right? That's practically 0 for all intents and purposes. Right? The probability of say 2 even, 38.7 squared e to negative 38.7 over 2 factorial, which is 2. Well, still that e to the negative 38.7 is so massively small, right, that it's still pretty small. You have to get up here around 20, 20, 25, 30, where you're going to have a big factorial there to overcome that e to the negative 38.7. But then you have probabilities, and then eventually the factorials are so big that it drives the probabilities back to 0. So you get shapes like this too. This is kind of a blow up of this one, right, just between 20 and 60. What do the probabilities look like? Gives us those probabilities. As the Poisson mean gets bigger, it's not an accident that it starts to look bell-shaped kind of there in the middle. Right? It's kind of a central limit theorem thing. You're adding together more and more small time periods, more and more things where in a really small time period you might only expect 1, 0 or 1. You add it together long enough, you get a few more. And so it's kind of a cumulative effect there. So let's, before we go on to talking about, we can talk about simulation, right? So in R, there is some commands for Poisson, right? So in R, there is a random Poisson values. So if we wanted to say get 5 values from Poisson, 3.87, it'll give us 5 random values. The way it does this is you have these Poisson probabilities, and there's the cumulative probabilities. Say 0 to 5 or 0 to 10. Right? You have cumulative probabilities as you go along. Right? The actual probabilities of 0 through 10 for this one are these values. So the probability of 0, 1, 2, 3, etc. And this P1 here is the cumulative. So the probability you're at 0, 0 or 1, 0 or 1, 2, right? And so the computer generates a random uniform number, continuous number between 0 and 1. And if it's less than this first one, it's going to call it a 0. If it's less than this one, but bigger than that one, it's going to call it a 1. And if it's less than this one, but bigger than the second one, it's going to call it 0, 1, 2, and so on. So it generates numbers. And this is the result of doing that 5 independent times. And if you do it a whole bunch of times, you can make a nice graph of it. Say we do it 10,000 times with a rate of 3.87, right? Then 0, 1, something like that. Another way to make a different plot is the bar plot that you can do. If you tabulate these numbers, it will put ones at 0, 1, 2, 3. It will actually get all the integers that you have. It doesn't look like maybe we had all the values up here, and it kind of made it a little bit funny. Alternatively, if you do this table command, so there's some 0s that occurred rarely, 7s or 1s that occurred a bunch of times. About 2,000 times out of the 10,000, we actually got 3 particles popping out of this thing. So you can simulate the data for different counts. But we're going to do a little bit of theory about expected values. Right? What is, so we are going to start with the probability function and ask what is the average value of y? For a random variable. The probabilities of y values are 0, 1, 2, etc. The probabilities are lambda to the y e to the negative lambda over y factorial. Probabilities of different outcomes. Right, and now we want to compute the expected value of y and show why it is actually just that rate lambda. Verify it. Right, so any of these expectations? Same thing as before. Right, we start with the basic definition to sum over all of our values of the value times the probability. So this works for our discrete random variables, the general ones, binomial, that is all we did with that same formula. And so let's put in our definition up here, lambda to the y, e to the lambda y factorial. Now we want to simplify that in a way to get to a simpler expression. Remember you with the binomial. The binomial also started at 0. So if it's 0, what does 0 contribute to the expectation? 0, right? So this sum is the same value if we write it going from 1 up to infinity. Same thing we do with binomial. It's something that, if that applies to other circumstances, it's something worth considering. It's a way to. But like the binomial, we can cancel something, right? We have y over y factorial. Right? These are all the products, but it starts with y, so we can cancel that one. So if we do that, we get lambda y, e to the negative lambda over y minus 1 factorial. Not every applied math thing that you would do with summations would have you do these two steps, but if these two steps are possible, they might be useful in manipulating things. Well, now things don't really look like Poisson again, because this goes from 1, and the y minus 1 factorial doesn't match the exponent here. Right. One thing we can do to fix that, fix the summation, is change, do a substitution. Maybe I'll call it w equals y minus 1. So if I want to decrease this by 1, I'm going to call it w and make it 1 less. This means then that y equals w plus 1, just rearranging that. Right, so this summation has to be the same value. If w goes from 0 to infinity, y is 1, and that's 0. If y is infinity, w is also infinity. What else happens? E to the negative lambda doesn't change. At any point in time, you could have pulled that e to the negative lambda outside of the summation, right? Like we did with just the probabilities. Eventually, we probably will do that, right? But y minus 1 is w, so that's w factorial. And now lambda, instead of being to the y, changing to the w, we get w plus 1. So it almost looks like Poisson again. It almost looks like those Poisson probabilities, except there's one extra thing. All right, the exponent on lambda is too high. But lambda is a constant with respect to the summation over y. Right? It's a number. Right, so we can pull one of those outside. So we can pull one lambda out. Make lambda to the w, e to the negative lambda, w factorial. What's this summation? You recognize these as the Poisson probabilities, just with another letter in there. Instead of y, it's w. Lambda to the w, e to the negative lambda, w factorial. That's a Poisson probability, and it's a sum over the entire range, so that has to be 1. So it's lambda times 1. And that's just lambda, which is good, which is what we're thinking it would be. So the expectation is, in fact, lambda. Right? But any questions? Sometimes parameters have this easy interpretation where we talk about it as being a range and it's actually the average, and that's great. For some, like the geometric or negative binomial, sometimes you get 1 over the parameter and it takes a little bit more to interpret. This one is straightforward. Right? Now the variance of this random variable is also lambda. Variance in general can be found as the expectation of the variable squared minus its mean squared. So you can do this one directly, but it kind of requires a couple times doing that change of variables to reduce it once each time. And so we're not going to do that, but it kind of follows the same manipulation style to make it work out. But anyway, the answer is that the variance ends up being lambda, and we usually think, to get back on the scale of counting things, the standard deviation is square root of lambda. This means that the expectation of y squared, just kind of undoing this, is the variance plus its mean squared. So this thing also would be the expectation of y, quantity squared. So the expectation of y just squared, that term, the variance is lambda, and this is lambda squared. So it's lambda times 1 plus lambda as the expectation of this thing squared. I don't have a particular rationale why you would use expectation of y squared, particularly in this case. In other things, if it's radius of a circle or the side of a square, it could have something to do with area. I don't have a particular application in mind here, but this is something that would come out of that. Now, in general, let's look at one more example, and then we'll do a little bit more. So we're sure that the mean is that parameter. Here's another type of example. Good. So the Poisson variable, besides some science things, also gets used as rates of rare things in different populations. So the Salk vaccine trials took place in the 1950s, 1954 or so, to try to establish that the polio vaccine actually prevented polio. One of the studies was a double-blind, placebo-controlled trial where grade 2 students in the schools, their parents and the children signed consent forms and agreed to get a shot. And if there was a randomization, either they got a vaccine or they got just a saline solution or something that would not do anything, right? And then they were evaluated at the end of the year to see did they exhibit any chance of having polio. Polio is pretty rare, right? So in the vaccination group, there's 200,000 children, about 201,000 in the placebo group. There was others who did not agree to participate. And out of those 200,000, there were 57 cases of paralytic polio. Oh wait, just polio in general. Right? The paralytic one was the most severe, could cause paralysis and death. But there are other ones that were pretty harmful as well. But 57 out of this number had polio, 142 out of this number. If you convert it to rates per 100,000 people, 100,000 children, right, it was 2871. If you converted it to rates per 10,000, then it would be 2.8 and 7.1 as the rate of the number of children. And I know that in Iowa, the largest school districts are around Des Moines and Iowa City are about 10,000 children. So if that rate applied to that school district, you would expect about 2.8 or 7.1, depending on whether they're vaccinated or not, to develop polio. Right? So this is a fairly rare event. You're counting kind of one at a time, and the Poisson model generally can describe probabilities associated with this pretty well. Right? So if it's 2.8, we could look at how many children would you expect in the district to have polio. Right? So the density for Poisson, say of 0 to 20 children, if the rate is 2.8, these are the probabilities. I can round those to say, 3 decimal places, and most of the time it's 0, 1, 2, 3, etc. Not much probability of having much more than that. On the other hand, if they're not vaccinated, right, the rate's 7.1, and then the probabilities of the outcomes shift toward the larger values. So this 11th entry here is actually the probability of 10 because it started at 0. So 10, 11, 12, 13, or even 14 children in the district having paralysis or very severe polio is really realistic, but it's not realistic in the vaccination cases. So Poisson gets used for a variety of applications. And so, have you heard any news about concerns about vaccinations recently? Measles vaccines have kind of gone out of fashion, but now measles are flaring up across the country. Right? So there's a shortage of measles vaccine because now people are rushing to get vaccinated because they skipped it. So the rates used to be low, and now the rates are climbing, and so it's more common than polio in this case, but still the kind of Poisson models might be used for describing the rate of cases and looking for change. What was important in this one that was the placebo-controlled trial, they did a different observational study where they didn't randomize, where they asked children in grade 2 if they wanted to be inoculated, if their parents and them would agree to get an inoculation. But then there's others, they just looked at the children in grades 1 and 3 and didn't give them any choice about whether they got it. They just used them as a control. Well, it was thought that there was probably some bias there because certain individuals would agree to participate. There was known risk factors associated with exposure to the disease. And so the individuals choosing to get vaccinated are probably different from the ones that don't. But this didn't have a control group that really was only volunteers. It was different between those two. And as a consequence, the rates were not quite as big between them. Now it looks like it's twice as big, and so that looks like a pretty big difference. But in terms of statistical testing, in terms of p-values and statistical inference, and how sure are you that it's absolutely not due to just random chance, this one was not really enough. The average across different things, if the rate was about 48, that was kind of the rate going on nationally about that time. So if there's really no difference between placebo and control, treatment and control, vaccine and control, right, then the rate would be about 48. And if it's Poisson, here are the Poisson probabilities. 54 in that one group is not so much different than the overall rate. The 20-something is a little bit low, but the other one was not so big. But in the randomized trial, 28 and 71, both of them were quite a bit different than the average rate in there. And so it was stronger evidence based on these probabilities for saying, yes, it stops polio. Right? And so then they could justify, with that stronger evidence, vaccinating 20 million children. Or whatever, and then probably 10, much more than that over the next 50 years. So that's a little bit of the story of Poisson, right? What we're doing here with these moments is what we're going to talk about next, kind of in a theory bit. But any questions about the basic distribution? So, probability distribution have characters which are described as moments. So the first moment is the expectation of x. The second moment is expectation of x squared. The third moment is expectation of x cubed, etc. And you could go up to any particular degree that you're interested in. Usually for probability distributions, the first few are relevant. Sometimes the central moments are a little bit more useful for describing things. So the second central moment is x minus its mean squared. Right? And that's what we call variance. So variance is the second central moment of a random variable. The third one is related to, so x minus its mean cubed is related to skewness and symmetry. Right, so this one equals 0 if a distribution is symmetric. It's greater than 0 if it's skewed to the right. And it's less than 0 if it's skewed to the left. And so the skewness, whether it's or symmetry, it's kind of captured by that theoretical quantity, right, for distribution. So if you had different probability distributions or different data sets, you might look at skewness. The fourth one sometimes gets used for measuring how heavy the tails are, or how much is it concentrated in the center versus spread. It's kind of related to variance, but it's a different thing. This one is called, so this is skew, a measure of skewness. The term for this one is called kurtosis, is the fourth central moment. Actually, these things usually get standardized because as you get a wider scale, cubing or taking it to the fourth produces very large values, right? A very wide scale, so usually they're standardized. Skewness is usually this thing divided by the variance raised to the 3/2. This is cubed, variance is already squared. This puts it on a scale without units, right? So if you have two variables, one's measured in, in kilograms, another way measured in pounds. The ones in pounds probably would have more skewness in this sense, just because the measurements are on a different scale. But if they have the same degree of what we really think about as skewness, like the picture we show, then they'd be the same. And this would adjust for the difference in units. Kurtosis, similarly, really is scale, because this is the fourth, and the variance is squared already. So squaring that takes out the units, and you just get kind of a pure number. The normal distribution has a skewness of 3. So relative to a normal, you have more probability out in the extremes. So it's often presented as that. We're not doing so much about that, but we've figured out the first couple of moments for the Poisson. The expectation of x was lambda. The variance of x, I told you, was lambda. So we figured out that expectation of x squared was lambda plus lambda squared, or lambda times 1 plus lambda. Right? But if you wanted the third and higher moments for this one to talk about its skewness or something like that, going back to first principles, you'd have to do the summation and do, for a cube, you'd have to do variable substitution 3 times to solve it. And it's just a little bit cumbersome. But there's a different way for that, and that's called a moment generating function. There's going to be a function that we have to calculate that once we differentiate it, will spit out these different moments that we might be interested in. So a moment generating function. Or MGF. We study this because it generates moments, but for a couple other reasons as well. There's a couple other useful things. For a random variable x, the moment generating function for this variable is some function of t. And it's defined as a certain expectation, an expectation of a function e to the t x. So it looks a little bit, what in the world's going on with this. Going back to the first principles of what the expectations are, we add up over all of our values of the value of this function here, times the probability that x equals that value. And this gives us something, right, some function. And it has some nice properties and some things that we can do. We're going to figure this out for the Poisson. That's the general page. I'm going to go to another page. So for a Poisson random variable, I'll say y is a Poisson. The moment generating function for this one is going to be sum over all of our values, so 0 to infinity e to the ty. And then our probability function goes in here. Right? Lambda to the y is negative lambda over y factorial. So now we need to simplify this then. Well, that's one thing. We can't change this, we can't really get rid of this 0 because this term is not 0. Is there anything else that we can do? You pull anything outside. Is there anything that's constant on every single term you're adding up? It's an e to the negative lambda. So we can pull that out. dy lambda y over y factorial. Okay, that's one thing to do. This e to the negative lambda is away from that. Now you can do, look, this has a ety and lambda y. They both have y up there in that exponent. We can actually combine things and just have a y exponent. So y goes from 0 to infinity. We can do lambda e to the t, and all of that to y. And that's inside of the, all inside of the summation. So what happens with this when you have a product raised to a power? All right, it's the same as those two pieces raised to that power multiplied together. Right? So it's lambda to the y, and then e to the t raised to the y. And when you do that double power thing, right, same as multiplying the powers together. So lambda e to the t raised up to the y is lambda to the y, and then e to the t raised up to the y. But when you raise to a double power, it's the same thing as multiplying. Because you have e to the t times e to the t times e to the t y times, and you add up those. In general, right, e to the x is the sum, x going from 0 to infinity of x. What? No, not e to the x. Like e to some number theta is theta to the x over x factorial. That's the general expansion, right? For e to a power. It has that expansion, right? So in place of theta here, right, well, I call it x. So we have a power, we have x factorial, but in place of that little theta thing there, right, we have lambda e to the t. So apply that expansion with theta equal lambda e to the t. Right? So what do we get? E raised to something. Right? E raised to lambda e to the t. If you combine those things and factor out lambda, right, it's e to the t minus 1. So that's the moment generating function for this. So a little bit of work to get that function. Now, one property of this is if we differentiate this thing with respect to t, and then set t equals 0, we get a moment. Okay. Yes?
Is it e raised to lambda times e?
Raised to the t minus 1.
Okay, so like the e raised to the t minus 1 is part of the exponent.
Yep. I can write it a little more. We have this lambda e to the t minus 1, and all of that is raised up to t. Kind of double exponent thing. So the property that this moment generating function has is you take the nth derivative of this thing with respect to t, and then set t equals 0, you get the expectation of x to the n. So it changes doing that summation and the change of indices and that substitution. It replaces that by taking a series of derivatives. So this is the function m of t. I generally like to put my random variable, I guess it'd be x. Let's change it to y. So the first derivative of this, right, with respect to t of this thing, let's call it m prime of t. We get the derivative of this thing with respect to t. Well, exponents, you get the same thing back, e to the t minus 1. And then you take the derivative of what's up there in the exponent. And so the derivative of what's up there is lambda e to the t. Right? And now we're going to let t equal 0. We put t equals 0 in there, e to the 0 is 1. Right? So 1 minus 1 is 0. So this first part is e to the 0. There's a lambda. And then e to the 0 is still 1. So we get lambda, which is the expected value of a Poisson. That works. How about the second one? How about the second derivative of this function? Maybe that would be, the second derivative with respect to t. Now, this thing, you have to take the second derivatives of this thing, that if I combine these things a little bit, I'll save a little bit of a step. So lambda and then e to the lambda e t minus 1 plus t. Right? I can put this extra e to the t up there, and then I just have it simplified a little bit. So when I take the second derivative, I'm taking the derivative of this thing. So again, there's a lambda. And then there's all that thing again, plus t. Then I take the derivative of what's up here in the numerator, exponent. So the thing up there in the exponent is lambda, the derivative of that. The 1 that goes away, plus 1 here. Now, a lot of practice using chain rules and things like that, exponents, yeah. We'll do some of this. That's some of the calculus tools of this. If you evaluate this thing here at 0, put t equals 0 in this equation, you get a lambda. And again, it's e to the 0 there. And then there's a lambda, and this one's e to the 0 plus 1. And so it becomes lambda times lambda plus 1, which was what we had as the expectation of x squared for that Poisson. So that the moments come out by taking derivatives and saying that things equal to 0. The reason this is working is that the e to a power had this expansion, right, where it was, to the 0 power, to the first power, to the second power. And so those things are in there in that expansion. And as you take derivatives, you wipe some of them out. Right? And so the next one that's not wiped out, after you take one derivative, you wipe out the constant, and you're left with the next one, which is to the first power. And you take a derivative again, you wipe out the second one, and the thing that's left is the second power. And so because of the expansion of e, you get these different but so it works. It gives you the moments. So instead of doing the summations, once you have the moment generating function, you can take the derivatives. Almost all of our probability distributions we'll deal with have moments. Most of them are nice enough to work with, and you can take derivatives to get moments and things like that. And you could figure out the third one if you wanted to, but I think we'll stop there. Are there any questions about these moments so far? There's a couple other nice properties about these moment generating functions. That the one we're going to talk about, two that we'll talk about right now, right? So it turns out that if a moment generating function exists around 0, that if the function that we've written down, this thing, if it makes sense near 0, then whatever distribution has that moment generating function is unique. Right? There's one and only one distribution that has that moment generating function. So if I tell you, if I know that the random variable has that moment generating function, then it is that random variable. one-to-one correspondence there. The usefulness of this comes in is if you have x1, x2, a bunch of independent random variables, and you want to add them up. And each of these have moment generating functions. Call it M1, M2, M to N for these. They can be different distributions, and this works. They can be the same distribution, in which case they have the same moment generating function. The moment generating function of the sum, if they're independent, is the product of the moment generating functions. So if we have a bunch of random variables that are Poisson or gamma or whatever we want to do, and we know their moment generating functions, and now we're going to add them up. Well, what distribution is y? What is that? How can we calculate probabilities for that without undue burden? If we multiply the moment generating functions together for those individual ones, and it's something we recognize, if it looks like Poisson, it is Poisson. Right? And the means add, we know that, so the Poisson rate is the mean, so we can formally show that it is a Poisson random variable once we know that uniqueness part. Right? So let's see how does this work out for Poisson. Right? So let's say x1 and x2 are two Poisson variables. How did I write it down? What I really want to do. I'll do two different. And one's lambda 1, and the other one's Poisson, with possibly a different rate. And they're independent of one another. So perhaps you have two school districts, right? Different number of children, different number of expected cases of measles, different number of expected cases of mumps or whatever. Right? And then you look at y1 is the sum of these two things. What is the distribution of y1? How can we calculate probabilities related to the outcome? Well, there's things that we can note before we do this moment generating business. Right? Well, x1 is an integer, right? And x2 is an integer. And these things both include 0, so the values of y are the same. Right? So we can get any integer for y. But what's the probability y equals one of those values? So our moment generating business tells us the moment generating value of y, generating function, is the moment generating function of the first one times the second one. And if they're Poisson, in here, the moment generating function of these things is e lambda 1 e to the t minus 1. And then the second one is e raised to the lambda 2 e to the t minus 1. Multiplying those two together because they're independent. So if we combine the exponents, it can be written as e to the lambda 1 plus lambda 2 e to the t minus 1. Does that look like a Poisson moment generating function? E to the constant number here, and then the e to the t minus 1. So this, on the right-hand side, is a Poisson moment generating function, the new value of rate lambda equals lambda 1 plus lambda 2. Right? Due to uniqueness, y, the sum of these two things, is a Poisson random variable with the rates together. So if you expect 3.2 children in one and 4.7 children in the other county or school district, and you're adding them together, 3.2, 4.7, you add those rates together, and it's Poisson, and you can calculate the probabilities for all your outcomes and mean and variance for those, right? So you get something pretty nice doing that. How else would we show that it's actually Poisson? Well, showing that it's actually Poisson otherwise involves a couple steps. But any questions on this argument? You have independent random variables, and you know they're moment generating functions, and you're taking the sum, or you multiply those, you see what it is, and if it looks like one that you recognize, it has that form, then you know what distribution it is, and you can calculate probabilities, means, and so on. Alternatively, so if y equals x1 plus x2, to show that this thing is at Poisson, and what is its lambda? Is its lambda. You'd have to do something like find the probability that y equals y. Right, if you can list out all the probabilities and give a probability formula, and it's the Poisson probability formula, then it's Poisson. But starting from scratch, you have to think about how x1 and x2 can add together to produce y. Right? Because what we have x1 and x2. And y equals x1 plus x2. Now x1 could take on any values from 0 up to y. These are all positive integers, so it works out kind of nicely that, the first count could be any of those numbers up to 0 through y, and we would not go past this value of y that we're interested in. But to compensate, and so the probability that x1 versus y, if the first one is y, or x1, right? Whatever the first value is for the first count, the next count has to be so that it adds up to, they both add up to y. So x2 has to be y minus x1. And so for the pair x1, x2, that would list all the ways that the two together can add up to that y. If they're independent, this is the up to y. x1 equals x1. We can multiply the probabilities. Independent probabilities get multiplied. And these are Poisson probabilities. 0 here, up to y. So that's lambda 1 to the x1 e to the negative lambda 1 over x1 factorial. Lambda 2 to the x2 e to the negative lambda 2 over x2 factorial. That's what the formulas are, right? Then we have to simplify this thing. Yeah?
Like, is that lambda 1 to the x1 and e to the negative lambda?
Yeah, this e to the negative lambda 1.
And
And this is e. This one, I'm sorry, this should have been y minus x1. And this thing should have been y minus x1 as well. Was this e to the negative lambda 1?
yeah, I see that.
And then e to the negative lambda 2, if they happen to have different rates. Right. So we're going to pull the e to negative lambda 1 and e to negative 2 out front. Right. That's constant in all those. That can go outside, and that leaves y going from 0, x1, sorry, up to y. And then we have lambda 1, x1, lambda 2, y minus x1. And there's an x1 factorial, y minus x1 factorial there. Right? We want to try to simplify this thing. We're going to multiply by something in the numerator and have it out here in the denominator. We have x1 factorial here and y minus x1 factorial here. That would be the denominator of a certain binomial coefficient if we had the right thing up top. Because x1 plus that is y. If we had y factorial up top, that would be a binomial coefficient. So if we have e to the negative lambda 1 plus lambda 2, y factorial, now x1 going from 0 up to y. If we put the y factorial here, and then x1 factorial here, and y minus x1 factorial here, y is the upper limit up here. The thing that's changing is x1. So y is not changing. Y always has the same meaning here and there. So you can put y in and out of that, and it doesn't change the equation. It's like having a sum going from 0 to 10, and putting 10, multiplying by 10, it can go inside and outside the equation. And then you have lambda 1 to the x1, and then lambda 2 to y minus x1. So this is one of these the combinations. Y choose x1 terms. So if I write it, I want to write it one more time, but I have to be on the next page. There's an e to the negative lambda 1 plus lambda 2. There's a y factorial out here, and this sum x1 going from 0 up to y. There's a y choose x1, lambda 1 to the x1. And then a lambda 2 to the y minus x1. This is one of these binomial coefficients. We looked at this in one of those story problems, right? Of what that is equal to, right? The binomial, like Pascal's triangle, was related to this thing. The thing that ends up being, y factorial, is lambda 1 plus lambda 2 raised to the y power. Does that look like a Poisson probability? The values y can take on are okay, 0, 1, 2, and so on, those integers. E to the negative lambda times lambda to the y over y factorial. So this shows with these probabilities that y is in fact Poisson, lambda 1 plus lambda 2 as its rate. So you can take your pick. Which would you like to do better? Do you like to do this thing? This is called a convolution method. For taking the sum of two random variables, right? and using this formula, or if I give you the moment generating function and you take a couple of derivatives, right? Or you figure out what the moment generating function is, multiply two together, and you see that again it's Poisson. It's kind of two ways of getting at this, but they're kind of different in flavor. Any questions about? one other example related to this. A Bernoulli random variable, say x of I is Bernoulli. So x of I with a little tilde means it has that distribution. The probability that xi equals 1 is p, and the probability that xi equals 0 is 1 minus p. How do we calculate the expected value of xi for one of these? Just as review. The value times the probabilities. So 1 times p plus 0 times 1 minus p, and it's just p. What's the moment generating function for a Bernoulli? Well, even the 0, 1 thing has a moment generating function. It works for them too, right? So the moment generating function, or I'll put an I for that one, right, is an expectation. So that was that expectation. Is an expectation e to the t x. We take the value times the probability plus the other value times the probability. So we replace just the 1 and 0 with that function of things. So we put a 1 in here. Well, there's t, the x is 1 times the probability. And then e to the t 0 times 1 minus p. So this is e to the t p plus 1 minus p. That's actually, I usually write it as p e to the t plus 1 minus p. A little bit easier for, I don't know, I'm used to seeing it that way, so. So if we take a bunch of independent x1, x2, dot, dot, up to xn are n independent Bernoulli random variables, and we take the sum x1 plus x2 plus xn. What is the moment generating function of y? We have the distribution. They're all going to have that distribution. Therefore, the moment generating function is this. The expectation takes x out of that, and there's just this t, this placeholder t there that could take on values that's in it. So every single one of these Bernoullis actually has this exact same moment generating function. So the y is the sum. The moment generating function is the moment generating function of the first one times the moment generating function of the second one times the moment generating function of the last one. And they all are p e to the t plus 1 minus p. You're going to get that copy in there n times, so it's just that to the n power. That's its moment generating function. Now we haven't figured out, is that the one for the binomial? It actually is the one for the binomial. We haven't quite figured that out yet, but that is a binomial. This is the binomial in P, moment generating function. So, by uniqueness, y is distributed as a binomial random variable. So there's kind of a proof here, right? This is the moment generating function of a binomial. We know the moment generating function of the Bernoullis. If they're independent, and we do the sum, then the resulting moment generated function is this thing. Right? And so by uniqueness, because this matches the binomial one, the sum does have that distribution. We can talk about means, variances, and other probabilities using the binomial formulas. It's valid to do that. If we take the first derivative of this thing, derivative with respect to t of this, what do we get? Well, now it's something to a power, so we're going to get n times that, n minus 1, and then you take the derivative of what's inside. The thing that's inside is p e to the t. Derivative with respect to t is that extra 1 minus p that just goes away. Now if you put 0 in there, let t equals 0, in this equation, what do you get? You get t times p to the e 0 plus 1 minus p raised to the minus 1, and there's a p e to the 0. This in here is actually just 1 inside. E to the 0 is 1, so you have p plus 1 minus p. That's just 1. And e to the 0, 1. And so what's left over is n times p, which is the expected value of 1. So this taking the derivatives and setting t equals 0 gets you back the binomial moments. We know those already, but it confirms that, right? So the final question, how do I know that that is actually the binomial moment generating? The last thing we'll do today, we want to confirm MGF of a binomial is p e to the t plus 1 minus p raised to the n. So how do we got to find this moment generating function. It's a special expectation. The expectation of e to the t times the random variable 1. Expectations for discrete random variables, the sum over all the values the variable can take. We have our function e to the t y, and then a binomial probability. We want to simplify this thing a little bit. There's not a whole lot we can do or correct this, and there's also not a whole lot we need to do. We need to combine something. I guess there's a couple different ways of doing it. Yes.
Could we combine the e to the ty and the p to the y?
Yeah, these two things both have the same. Well, they're both raised to a y exponent, kind of like like we do with cosine. These things can be put together. That leaves n choose y. P e to the t. That thing raised to the y, and then 1 minus p raised to the n minus y. And another version of binomial coefficients. That story that we had the x plus y to the n and we did the binomial expansion, it's that same thing again. So it's a useful identity. So if you take p e to the t plus the second term, 1 minus y, raised to the n, right, this was like saying, we have a plus b to the n. It's a sum of k going from 0 up to n of n choose k, all equal replaced it with y there. A to the k, and then b to the n minus k was the general binomial coefficient thing, right? And so I replaced k by y because that's my random variable, and I made it specific to that. And instead of a, I have p e to the t, and instead of b, I have this 1 minus p. And that's it. That's the moment generating function. So it looked kind of messy, but it didn't take that long. Because if you can see combining the things with that coefficient there, right? So the p e to the t raised to the y. You distribute it, so you get t to the y, e to the t. I know I wrote this something like this before. And then the double one is ty, and that's what we had back over here to get that. So we get this moment generating function. The same moment generating function type of argument works adding up geometrics. You get a negative binomial, there's a correspondence there. All these random variables we have, they have these moment generating functions. Arbitrary, discrete ones have moment generating functions. They're not necessarily quite as useful because it's not kind of a simplified form. You just kind of have a list of e to the ty times the probability, and if it doesn't simplify very much, it just doesn't help you all that much. But though it does exist, right? There's another use we'll have with moment generating functions when we come to continuous random variables. There's something very useful with scale changes like linear transformations of variables and figuring out what exactly is the distribution of our scale variable. And moment generating functions have a use there too because of this uniqueness. But that's it for today. That's really what we're going to do. But any questions about? So yeah, so one example where we get a new variable to deal with, and then some theory to go along. And if you have the homework before, I can really drop this off at 4.
Yes, I've heard it before, and it's always worse than I expect.
Did you tell her the punchline or did you figure it out?
She's heard it before, that's why she just said, you really hope this.
Well, no, right. Well, like she said it.
Yeah, we did, like.
I just didn't, well, it doesn't mean that you remember the punchline.
There's a paper clip right there.
What? Our college would be becoming an adult, but I'm just gonna go take a nap like a child.
That is what becoming an adult means.
Thank you. Yeah.
I don't know if I put this in.
Is it the colder corner?
Yeah, or there's a paper clip.
Oh, thank you.
I one of those two.
Somebody else left here.
Perfect.
Thank you.
Yeah.
And then like 4C was asking to compute the mean and the standard deviation, but like when I used that, I just put that in as my code, I put that here. But it just didn't look right that they have the same mean as somewhere all the way up in the test result.
Uh-huh. It might be a little bit
I
high, you know, if it's, yeah, I mean, it look like that. I mean, you might just make a note saying that it should be, I think it should be closer to the.
Yeah. Or I wasn't sure, did you want us to compute that or did you want us to eyeball that one?
You can compute it from the formula, like the R times 1 minus P over T. Would be the formula for that
Okay,
one.
that's like one.
Yeah.
Okay. All right.
But, you know, you can do what you want. You can either just make a note of that, or if you want to correct that one part, just slide it into my door. I'm not going to get back to the office right away.
Okay.
Or just write a note that.
Yeah, I got this key right now, so I
Oh,
don't know if I'm
okay.
gonna have time to correct it.
Sure,
in
sure,
time.
sure.
And then the another one, the standard deviations here. I didn't quite. I just did the n times p times the 1 minus p for the standard deviations in 1.
Yeah.
And I got that for E, but when I like started getting into F, where it was like
The different parts, yeah.
yeah, I think I did that. I don't know. I just did 0 because for some
Yep.
parts. That
Yeah,
is
yeah,
okay.
yeah.
Cool.
Because if there's $800 coming in every single time.
It's a constant,
It's a
which is
constant.
like what we talked about
Yep.
the other day.
Yep.
Cool. Perfect.
Gotta get out there before it rains again.
No, seriously. Thank you. Have a good. No, I'll see you tomorrow.
Yep.
We'll be here.
you?
Hi, good. How are things? What's your name again?
Megan.
Megan, yeah. Thanks for coming.
Thanks for holding this.
Hi. Hey, how's it going?
Good, how are you? Thank you.
Yeah.